So the other thing that you need for your homework is the database code. So I'm going to give you just enough of the database stuff for you to do your homework. There are separate database courses here in our curriculum, so I don't want to go too much into it, but I do want to give you just a high-level overview of databases so that you can do your homework. So initially, we had these relational databases that stored our data, and the query language that was used to interact with these databases were based on mathematical logic. And I sort of escaped math to come to CS. And if you're in CS and you're trying to do mathematical logic to get your data out, you're like, well, I didn't escape very far. So that's where these folks at IBM, SQL and Boyce at IBM Research, they were like, you know what, let's make a language that is more human readable, that can allow people to do the same mathematical operations onto the database as the mathematicians were doing. So this is a query language, and it was hugely successful. So this thing, I think it was in, so 1970s, all throughout the 70s and the 80s, this was the thing to learn if you wanted to do databases. So DB2, Oracle, SQL Server, PostgreSQL. When the databases were first developed, IBM is serving a whole bunch of financial institutions, and financial institutions need their data to be consistent all the time. So what was developed as part of these SQL databases were these properties. It's the ACID properties. So the transactions can be made atomic, meaning that they're fully completed or they're fully not. They all fail. They are consistent at all times. The system must remain in a valid state, and any errors that you have, so say you're trying to do a complex interaction with the database and one of the things fails, everything else has to be rolled back. So that's another property. Isolation means that each transaction will execute as if it's the one and only transaction in that database. And then durable, the changes are permanent. But in the 80s and the 90s, the internet and the World Wide Web happened. And so with the World Wide Web, we have a change in the kinds of data that people are trying to access and process. So you have this high volume, high velocity data. There's tons of data coming at you all the time. And not only that, it's non-uniform. It's dirty. It's all different kinds of formats. The data has errors in it that need to be cleaned up. Totally unlike what you had before. And if you were trying to handle all of this in a traditional database, you were going to suffer effectively. The other thing with World Wide Web data is that the ACID properties aren't required. You don't need transactional properties when you're handling web data. And this motivates a move to non-relational databases. And you'll see non-relational databases pretty much everywhere in the cloud. There are still people who will run SQL servers, but for the most part, a whole bunch of people are running these non-SQL things. And so this is where the term NoSQL came from. You're using other approaches other than SQL to do your data. So NoSQL consists of really large-scale databases with no standard query language. It's often schemaless. So the idea is to have key value storage of arbitrary types. This is similar to the Python dictionary, right? Where you saw with the dictionary, the keys could be any data type, and then the values could be any data type. This is akin to static typing, which is what SQL wants, versus dynamic typing, which is what NoSQL gives you. And this was very convenient for a lot of people. And then the other part of NoSQL is that it didn't provide you much in terms of querying support. So with a lot of NoSQL, especially web apps might need simple puts and gets of the data, like for a user profile. It doesn't need transactions, it just needs puts and gets. So this is where NoSQL has been an advantage. And then the consistency doesn't need to be ACID. So there's this other acronym called BASE, which is basically available, soft state, and eventual consistency. almost all of the web data can be classified as base. So this is, the example is DNS, right? DNS, I don't need strong consistency amongst the users for that particular name. I just need eventual consistency so that whenever I move my website from one IP address to another, eventually everybody goes to the new website. But I don't need to strictly force everybody to change over at the exact same time, is the idea. And this happens all over the place. Like for example, like high scores in a video game. I don't need everyone to see the exact same leaderboard, but eventually the high score should be known to everybody if the thing quiesces long enough. Okay, the real benefit of NoSQL is because you're getting rid of the ACID properties, you can get performance and scale galore. And this is why people were adopting NoSQL databases in the early 2000s, in the 90s and the early 2000s. Every NoSQL database will give you a different set of properties. They've optimized for a certain use case, and this is why there's a spaghetti soup of different NoSQL database backends. And this is a site that summarizes some of them. So if you click on this, you can see all the different systems that are out there and what their target was. What problem was this database backend attempting to solve? And you can get that from that URL, or you can, I believe this is covered in our database class and in the cloud and cluster course that's happening this quarter, I believe. Okay, so this is a comparison of SQL versus NoSQL and the different properties. And so this isn't to say that that SQL isn't being used for a reasonable thing, but it just shows you that the explosion of the different kinds of applications requires you to have different backends for each application. Might have you. So there's been this push is, can I get the best of both worlds? And that's what NewSQL is all about. This is my thing, Revenge of SQL. The idea of NewSQL is to take SQL features like ACID properties and try and bolt them onto NoSQL without too much overhead. So that's one thing. And so people have been putting SQL interfaces on top of these large-scale data processing engines, Hadoop and Spark. We'll do a little bit of this at the very end of this course. The other thing that people are doing is they're going to bolt NoSQL features onto regular SQL databases. So try and take a SQL database and horizontally scale it is another approach. And this is what HStore and Spanner are trying to do. We don't have a lab that does this, but if you, in your Google Cloud Platform project, you can create Cloud Spanner, which is this horizontally scalable SQL database that you can have replicas running everywhere, and then it gives you transactional properties. So this is why the thing is so expensive. Like if you deploy a Cloud Spanner instance, it's going to cost you a bunch of money, but it's going to give you the properties that you want for a business. So definitely on the enterprise, definitely for financial institutions, this kind of thing is needed. You need scalability and transaction properties. And that's what NewSQL is trying to do. Okay, so the idea of NewSQL is to get the best of both worlds, get the SQL querying and consistency, get the NoSQL scaling. And so there's this article that I came across last year where they compared the narrow waistline of the protocol stack, where IP is the interoperable piece between all of these disparate applications and all of the disparate networking infrastructure underneath. This person makes the case that SQL is now the narrow waistline for data processing. So you'll have all different kinds of tools and applications at the top. They will all, in the middle, speak SQL, and then you'll have a whole bunch of backends underneath that will support those queries. So this is why maybe learning SQL is a good thing versus these random NoSQL languages that are out there, which are a dime a dozen. So it's an interesting article if you want to read that. Okay, so I'm going to briefly go over SQL and most of the parts that you need for the web app. So the SQL stands for Structured Query Language. It includes two things. There's a data definition language and a data manipulation language. We're going to need to do both. We'll start with the DDL. The parts of the DDL we're going to talk about are the two for creating and dropping either a database, a table, or an index. So these are meta operations on your database itself, whereas the DML are databases inside of your data. The DML are operations within your database. Okay, so the first one's create database. This is what you would send a SQL backend to say, hey, I want to create a new database. You connect up to that database backend, say create database, and you give it a name. So if I did this and I sent create database mydb, this creates a database called mydb on the backend, and then I can instruct the database server to use that database for subsequent queries. I can then, on that database, I can create a table, and I have to specify when I create a table all of the types for the columns that I want to insert into that database, such as this. So I'm going to create a table of persons, and then the ID is an integer. The first name, last name are characters of 25 characters each, and I have to statically specify every single column in that database, in that table. So some of the basic data types. So again, this is just like strong and statically typed languages are bytes, integers, long, singles, doubles. There's a huge table of these as a reference in one of the links that I'll have at the end. The second thing that you'll need is the data manipulation language. And typically in a web app, there's this acronym called CRUD. And this means that your database backend needs to be able to create entries, read entries, update entries, and delete entries. So for SQL, the DML, the commands for doing CRUD are insert into, select, update, and delete. So and these are the things that you would use for your web app, especially for creating and reading for your site. Okay, so select is used to read from a database. You can basically specify a column name and a table that you want to read the column from. And the result that comes back from this query that I sent to the backend is basically another table, and it's called the result set. So here's an example. I have a persons table. It's got these columns in it. And the select, I can say I want to select the first name column and the last name column from this persons table, and it'll give you this table back where the first name and the last name are given, and then each row corresponds to a row in this database. If I do a select star from persons, I'll get the entire database back. This is basically what you need because you're going to get all the bubble tea shop things from your in the viewer. Okay, I can narrow down what I'm looking for with the where clause, and this is just a predicate that you apply onto the results that will filter out the things that you're not interested in. So this is a syntax: select column name from table name, where column name value or column name has some kind of operator to its value. So here's an example: select star from persons, where the city is this city. Sandies, this is, I guess, in France. And then you'll get this back, right? So the city matches that where clause. Insert into, again, if I have this as a database and this is a table, then I would just insert into persons with the values keyword, and then I would specify every single column as part of this insertion. And then you would get something that looks like this. So that's insertion, and this is what you will want to do for your homework, right? I'm going to get a form submission. It's going to have a whole bunch of fields. I'm going to have to turn that into an insert into. And so your backend for homework 2 is SQLite 3, and SQLite 3 wants to speak this, SQL. So this is where you're going to take your web app and transcode it, or turn that web request into this insert on the backend. Update is used to update records in the table. So if the entry already exists and you want to just change its values, you will use this SQL. So if this is my my table, and if you look, there's a couple things here that are null. They didn't get initialized, so maybe I want to update those two columns. So if I say update persons, set the address to this address and the city to this address to patch up these two entries. So I patch up the ones where last name is this, which I can't pronounce, and first name Jakob, then this will give me that. Okay, so that's the update. And then the last one is the delete. Delete from that table some where some column is equal to some value. So if I have this as a table, delete from persons where the last name is this, the first name is that, and then it'll just delete that column. So as a stretch goal, being able to delete bubble shop entries would be nice to have in your web app. Okay, there are other SQL primitives that you can use, but you don't need any of these for your web app. The reason why I'm showing you these things is because when we get to the very end of this course and we talk about things that you want to do with the data, like operate on them, it's basically trying to emulate the things that SQL is trying to do with the results as well. Let's see. I'll get to that later. So this is, I'm going to revisit, well, this is version 3 of the Guestbook app. And version 3, it doesn't derive off of version 2. Version 3 derives off of version 1, which was the MVC pattern. So the reason why I'm adapting this from version 1 is because I want to show you how to swap out the PyList backend with a SQLite 3 backend. So that's the only thing that's different, is that I am, and this is the one that you're deploying in your lab. And so the SQLite 3 model is in this Python file, and this is what you're going to change to add your own model. And then one of the things with SQLite 3 is that it will use a file in the file system to store your database. So I will show you this, and actually this SQLite 3 is used everywhere because anybody who's got an iPhone has a bunch of SQLite 3 databases in there, because that's basically the standard storage that most apps are using to push stuff into the phone's data store. So this is the model SQLite 3.py, and the first thing that you'll see is that it's got this init. So this is the constructor for this model. Well, the first thing on there is that where am I going to store the database, the data? And so I mentioned earlier that SQLite 3 stores it in the file system. So this is going to create a file called entries.db to store all of your entries. And then you can see that this model, this version of the model, is going to inherit from the base class capital model. And it's got this initializer, and the initializer, what it's going to do is it's going to instantiate right on startup. So when someone does an import and this thing gets instantiated, then this command is going to run, and what it does is it wants to make sure that the database exists. So it's going to connect up to this database file. So SQLite3.connect says, where is the backend data store? Connect up to that, and it gives me a connection. And this is emulating what a SQL server would typically do. I'll set the cursor, which is where I want, sort of where I'm going to execute the commands from. And then I'm going to try to do an execute of select count from Guestbook. And this is to check to see whether or not that file has been created and whether or not there are any entries, whether or not there's a Guestbook table inside of this database. And if I try this and I get an exception in a SQLite 3 operational error, that means that that table doesn't exist in that file. And then this command will then create that table for me and give it the data types associated with each of the columns in that table. This is something that your app should do, right? If the bubble T database doesn't exist, it should automatically on initialization create that file, populate that table, so that the subsequent interactions by the user will just work. And you don't have to put that error checking code in your regular stuff. And then it will close the database. So this is the select code for SQLite 3. It connects to the database file, gets the cursor, and then just has the cursor execute select star from Guestbook, and then does a fetch all, and the fetch all will return all of the entries in the rows as a list of lists. And if you recall, that was our interface for the model. All the entries as a list of lists, and then this will get returned to your Python code to populate the template. The other thing is the insert. And so for the insert, I have these 3 parameters. And the way this is implemented is I'm going to create a dictionary with these parameters, the name, email, and message, and then the fourth parameter I'm going to insert as the date. So I'm going to insert the timestamp for when I got the guestbook entry. I'm going to connect up to the database, get the cursor, and then I'm going to execute insert into the guestbook these parameters, name, email, signed on, and message, with the values that are pulled from the parameters from that dictionary that I just gave you. Okay? And then I'm going to commit these values to the database and then close the connection and then return true. So again, this is implementing that abstract class that I had earlier. If you'll note, this is the correct way to do the insertion. This is using parameterized queries to avoid the SQL injection vulnerability. So if you've taken the web security classes, I have like a week or 2 weeks on SQL injection. This is a pattern that you must use when you're doing the insertion. You don't want to do an insertion into guestbook and then use this directly, because this will allow someone to actually insert SQL commands into this string. So this is an example of a parameterized query. Are there questions about this implementation and what you'll be doing? Yeah.
Just you need to create a row ID, or is that created? That's just what you were initially. That can fail every time if you don't have one.
A row ID. I think the ID, the entry might be incremented. Oh yeah. That's a good question. I don't know. I don't know if row ID is automatically inserted by SQLite 3. I assume so. It is? Okay. It is? Okay. Okay, the next thing I want to talk about are SQL functions. So SQL has these aggregation functions that operate on the table that you apply them to. So here's an example of, I want the average of all the values in a particular column from a particular table. And so in this case, if I do average unit price from the products, then what this will do is it'll take the unit price, average them up, and give me the result back. I can use this within another query to say, give me all of the products whose unit price is greater than that average, and then it will return mascarpone. Okay. So the issues with doing this, if you can think about an enormous table with a bunch of data that keeps on having entries added to it, this is a problem with SQL databases. This is very painful for a SQL database to go through if you have a massive amount of data that's continually being updated. So we call that a fire hose. And fire hose data sources is what we have on the internet. Like, the data doesn't stop. And so can a database scale to store a nonstop fire hose of data? And then can a database handle queries and functions on top of that fire hose? So this is an issue. And this was the issue that Google faced when they were trying to build their initial search engine in the 90s. They couldn't store all their documents in a SQL database and then hope to be able to build indexes and queries on those to support search. They needed something else. And so this really motivated them to go into a non-standard data storage. So in their case, there's this paper on the Google file system, which talks about the design of a data backend that rips out all of the things that you would normally have for SQL. It also forced them to do non-standard querying and parallel data stream processing. Like, you couldn't just with a single thread go and find the average of all the data, because you're basically going to walk through all of the data using a single thread. You actually need multiple threads, and then you need to have a combination step at the end. This is what MapReduce is. So they designed a different way of doing this querying, and this is what they used to generate their search indices that ended up giving them the market share that they got for search. We're going to talk about this because this is where the heart of data science is, right? You're going to have a huge data set that keeps on getting added, and you need to be able to process that and query it in sort of near real time. And then these are organizations of data computation that we're going to look at the very last week of this class, hopefully, if we can get through this content. Okay, so the next couple of things that I want to talk about are ways to avoid writing SQL. So this is why there's like 6 to 10 slides on SQL, because people don't like writing SQL. They would rather do something else, and it'll be actually, I think it's going to be rare that any of you do actual SQL programming, but maybe I'll be wrong. One of the things that people like to do is, hey, I don't want to learn multiple programming languages. I just want to learn my Python, and then just have the Python, translate the Python into SQL. So this is called object relational mapping. And so these things are called ORMs. And the idea of ORMs is to take objects and then map them directly into the relational database, right? I have a structured object that's got strong types. Can I just put that into the database, into a table? The table's got strong types. It's got a table name. I have a class name. I'll just push it into the database. And the idea here is you're going to sacrifice a little bit of performance as the ORM does a translation in order to get this sort of the easier development times for an application developer. And that's the idea. Okay, so the benefits of an ORM is that you don't have to learn a second language. You can potentially clean up your code, although the code I'm going to show you might be a little ugly. Minimal SQL injection. So because you're not writing SQL statements, the programmer isn't, then there is no chance for someone to insert a stray SQL command inside of your processing. And then it will unify the insertion, the querying, the updating, and the deleting from any database backend using something like Python, right? And so all of the examples that so any of the Google Cloud backend database APIs, you can access those using the native interfaces, or they're typically Python bindings that allow you to just write Python code to store stuff on the back end. In fact, when we go to the serverless version of your web app, these are just Python calls that you make to the back end, and the back end is just happily, reading your data, storing it, and then producing it back to you with just simple API calls. Okay, so here is an ugly example of create table. I have 2 tables, a person and an address table. And then I'm writing native SQL here in the middle. That's what's in green. I have to create these SQL statements and then send them to the database backend. Here's an example of an ORM. So this is SQL alchemy, where I say instead of this table declaration, this create table statement, I am going to define the table as a class. So here is the person class, here is the address class, and I can define this all in Python to be certain data types. And then what I'm going to do is I'm going to take these as bases and then just say create all with this engine that points to this database file. So there's a SQLite database file. And then this will do the creation of the tables. So 2 ways of doing the exact same thing. One is more Pythonic, one is all Pythonic, and the other one forces me to know Python and SQL. So that's the idea of an ORM. Insertion is similar. So at the top, I'm inserting using regular SQL. And on the bottom, I'm creating a new person and saying, add that person and commit. So this is potentially more straightforward to a Python developer than doing that, because the Python developer might not understand what SQL injection is. And this is where the disconnect is, where a novice SQL programmer will easily give you a security problem by trying to write native SQL. Querying is similar. Rather than doing a select, you create a session and then you do a query.all. And you'll see for the NoSQL database backends that Google has, you'll see the similar syntax. So when we do the cloud data store and you want to get all of the keys in your data store backend, you can do a query.all and it'll give you all those keys. Or sometimes it's a scan. It'll do, database table.scan, and it'll give you all of the keys and all the data entries. Okay, another thing that people like to do is they like to write URLs instead of SQL. And then this is what REST and JSON is all about. So REST and JSON are ways of, and we covered this when we talked about the web frameworks, right? The model is basically running on the back end, and the controller and the view are on the front end. And the way the controller and the view are trying to access the back end is through a REST API. And that REST API is doing the CRUD operations. It's doing the create, the read, the update, and the delete. So you're not really doing SQL anymore. You have bound, this is where the presenter view comes up, right? You have bound a URL to a particular operation, and then that's basically how you're changing the data on the back end. Okay, so this is writing URLs instead of SQL. And so the idea is to programmatically call into the database via web APIs or endpoints. These are interchangeable, like web APIs and endpoints are interchangeable names. And so this is basically directly interacting with the model on the back end. And this is being used everywhere now. This has exploded recently. So here is a picture of the number of web APIs per year. And you can see this thing, it's up to like 18,000 of these things. With each API, and so when they talk about DevOps, people are pushing out versions of their APIs like a couple of times a year. So you have all of these endpoints that are being sort of distributed. One of the problems with doing this is that you're giving people access to the model, right? Like with your API, you better make sure that's secure, because if that's not secure, then all of the issues that we have in web security show up in your backend web API. So here's an example where Nissan put a bunch of web APIs up, and then it had a security issue that basically allowed someone to remote control the vehicle's functions. So if you're driving a Leaf? If you're driving a Leaf and then someone is basically discovering your REST API endpoint that your Leaf exports, then they have control over your car. So people need to think about the security of the API and the authentication. The FCC had an API that was up there that allowed anybody to upload a file to the FCC website, and it was obviously you could upload malware and try and get the FCC to run it. And then the worst one was Instagram's API that exposed Justin Bieber's rear end. So then you know Instagram's got a problem when that happens. Okay, so for web APIs and endpoints, there are two parts. There is the API itself, which is either REST or GraphQL, which we'll talk about. And then the other part is the data exchange format. How are you going to get data to and from that endpoint? And that's going to be either JSON or gRPC. So the first thing is the REST APIs. REST stands for Representational State Transfer. And this is a style of web software architecture that simplifies the application. It's not a standard, but it's a design pattern that everybody is using. Every web API, every web sort of property has a REST API interface, more or less. And the idea is to take all the resources and the operations that you want on those resources. So for example, data, files, and any of the functions you want on those data and files. And you identify each resource and the operation as some kind of URL. So everything is a URL. The method on the URL selects the kind of action that you want to perform. And then the URI, the path, specifies the resource. So this is a picture of what a REST API has. Whoops, I guess I can't do that. It has a URL which specifies where. It has on the bottom left what. So this is what happens when you hit this URL, and this is application defined. And then on the right, it's what kind of how to do the operation, and this is where the HTTP method comes in. So here is a REST toy example. I have my REST API at foo.com, and then I export a URL that says /users, And the semantic that I define is that my service is foo.com. The database that's being accessed is the first part of this path. And this is just something that I come up with. I'm going to take the first part of the path and say that's the database the person wants to access. The table in the database that person accesses is users. And then when anyone hits this URL, it's going to go to that database, go to that table, and then return everything that's at that table, in that table, the users table. And then typically the users table is returned in a particular format, so it could either be XML or JSON. And then this is basically what's happening is that you're turning this URL into a pre-canned SQL statement. You're saying select star from that table and then return it as the data. And this is much easier. I can just wget that or curl it rather than having a SQL interface to that. Okay, so Twitter, Flickr, Amazon, and everyone else that might have a REST endpoint. So with REST and HTTP methods, the request method is going to determine the kind of operation that you want done on that resource. So there's a get, which just gets a representation of the resource that you're accessing. And typically, when you use a get on a REST interface, it should have no side effects. So these are side effect-free, safe operations. Then there's the post that submits data to that endpoint to be processed. And that's typically through an HTML form that you would submit that through. And there's a put that will upload a resource onto the API. And then finally the delete. So these are HTTP methods that you can use in a REST interface to do specific operations on the back end. Okay, so there are some issues with REST. One of the problems is that the developer ahead of time has to specify the mapping. Like you have to define an interface to your backend and then map a whole bunch of URLs to that interface that you want to export. So if you go to for example, the Twitter REST API documentation, it's enormous. There are hundreds of REST API endpoints on Twitter. And so developers need a new sort of piece of functionality. It gets another endpoint on Twitter. And then this is where you've got a whole bunch of basically web crud out there. Another problem with REST is that you can have this problem of overfetching. The API, because it's statically bound to a particular query, if you want a very specific piece of data, and the only way to get that is to fetch an enormous blob on a REST endpoint, because that's the only endpoint that data exists in, then I'm going to do this overfetching operation where I'm going to grab a whole table only to get one entry, right? And this is not, I don't have a where clause in a REST API. You know, like with the select, I have the where clause to reduce the results. I don't have that on a REST API call. The other thing is underfetching. So if I have multiple queries that I want to do, I have to send two individual queries to that backend, right? Why can't I just send one set of two queries and then have the backend give me two results? So that's another problem with REST. Another big issue is that it slows down DevOps. So now the front-end developers, if they need to implement something new, they have to coordinate with the back-end engineer, the ops teams, to make sure that deployment can happen smoothly. And so this slows down your development cycle and the deployment cycle a little bit. Okay? So this motivates GraphQL. So this is from Facebook from 4 years ago. And the argument with GraphQL, and this isn't quite a hot standard yet, but people are using this more and more. The idea is that the REST mapping to a SQL query is way too coarse. And the static mapping is problematic. And so basically, instead of, you have this issue of overfetching and underfetching, and then you have this issue of needing multiple queries for multiple requests, or multiple queries when you want data from multiple tables. And so what GraphQL does, this is a language that allows the client to specify a little bit more of the details that it wants out of its query. And it basically is making your front end a little bit more programmable. Gives you programmable control over what you're asking the REST API endpoint to deliver you. And the idea is that it might reduce the load on the back-end REST API that's servicing your requests. So this is akin to giving SQL-like interfaces to your back-end data, which you have to do this right. Otherwise, you also have a problem with security on the back-end. Okay, so here's an example of a GraphQL query. Say I have this user table, and the only thing I want in the user table are these columns: balance, email, and subscriptions for this particular user. Well, I would rather do this than grab the user table, get all of those fields, and then whittle down what I want. So with this query, I can just get those things for that particular user. And then if I have a query where I want information on 2 users, then rather than doing 2 REST API calls, I'll do 1 GraphQL call, and I'll ask for this user, and I just want their email addresses. And that potentially will save you queries on the back end. Are there questions about GraphQL and what it's attempting to do? Okay, whether or not it's going to do that, I don't know the prevalence of this yet, but I think it's still not widely used. Okay, so I mentioned before, one part is the API and the endpoint, and the other part is the exchange format. Almost all of the REST APIs are giving you what's known as JavaScript object notation. This is the de facto web object data format. It used to be XML, but XML is no longer being passed around very much. JSON is a subset of JavaScript, and it's easy to parse and generate. It's designed to enable this stateful real-time communication between the browser and the web application. And it's often used with AJAX. So AJAX is asynchronous JavaScript requests from the browser. And it allows the client and the server to communicate data back and forth to each other. So AJAX stands for asynchronous JavaScript and XML, because when it was first being done, the interchange was XML. But now we have mostly JSON going back and forth. So this mechanism has this other acronym, AJOJ, which is asynchronous JavaScript and JSON coming back. Okay, so this is the sort of the format of a JSON object. These are unordered containers of key value pairs, very similar to Python dictionaries, but in JSON, the keys are all strings. And the values are all JSON values, where JSON values are very specific things that we'll talk about in the next slide. It's wrapped in the curly braces, much like dictionaries. So not like dictionaries. The key value pairs are separated with commas, and the colon separates the keys and the values from each other. So that is like a Python dictionary. And then this is parsed into whatever native language you want to operate on JSON with. So you would take the JSON notation, and then if your backend is, or your front end is Python or JavaScript or Ruby, you would just have some library that would take JSON and parse it into a data structure that's native to your programming language. These are what JSON values are. So they are strings, which is a sequence of 0 or more Unicode characters wrapped in double quotes. They're numbers, either integer or floating points. There's no octal, there's no hex, there's no not a number, there's no infinity. It could be a Boolean, which is true or false. It could be a null value, that is spelled out null. And then it could also be another object, so it's recursive. You can have a JSON object as a JSON value. And then arrays of objects are also considered JSON values. So it has a very specific syntax that you'll see. So here's an example of a JSON object. Curly braces defines it. All the keys are strings, so first name, last name, and address. You can see that this address has a value that's another JSON object. And this JSON object has a bunch of key values pairs that are all strings, and then one that's actually an integer. And then it can also, the object can be a list. So in this case, this is a list of strings. That is the value for that particular JSON object. Okay. Other questions about JSON and parsing it? Okay, so that's what we have with the JSON object. Okay, so this is a common pattern. So when you, in your final project, you'll be adding a bunch of REST API calls to your web app. This is a common pattern. Maybe you're going to use requests to access an API endpoint. And then I'm going to do a request.get of that API endpoint. So this is an advice API. So you keep on hitting this thing, and it gives you a string that's the advice of the day. And then you will take the response, and you say, you know what? I want to parse that. This will return. Oh, thank you. Where's my pointer? I'm not going to search for the pointer. I'm almost done here. I'm going to take the response, and I'm going to parse it with the JSON. This is one way of parsing JSON in Python. There's a JSON parse method as well that you could also use. But this is going to take the result, which is given as JSON. This API endpoint will deliver JSON. And then you're going to parse it, and then the result of that parse is going to give you a dictionary. And then I can just index the dictionary using the keywords that are, so I would have to know the format of the object that I'm getting from the advice thing. But then I can just use this thing directly in my web app. So this is what your final project will be about. You'll be accessing any number of web APIs. You can do it through a REST interface, or for Google Cloud, if Google Cloud gives you Python bindings, you could just call the API with Python code if you'd like. So there's multiple ways of integrating a web API into your app. I'm just showing you the way to do it with REST and an actual request. Okay, so there are some issues with JSON. First of all, it's a text format. So if you have a bunch of binary data that you want to pass back from your endpoint, that's a total haze, because that is a really inefficient encoding. And so, moreover, in order to send back binary data, you'll typically base 64 encode it. So for this means that every 8 bits that you send gives you 6 bits of actual data when it's base 64. So that's an overhead that you would like not to have to pay on every single request. So if you're Google and your BigQuery database is passing back JSON, that's a lot of overhead to be paying network bandwidth, server resources. The other problem with JSON is that this flat format, and the object is treated as a string. And the string, you're going to walk through the string linearly and parse it. So this is also an expensive step. For example, I get a huge JSON blob back from a server. That JSON, this operation is going to linearly go through that thing as a flat string, and then try and give me a structure on top of that. So that's something you would like to avoid. So this motivates gRPC. This is initially developed by Google as it's called a protocol buffer. The goal here is to support serialization of structured data into an arbitrary format, and this format is going to potentially be binary. So I'm not going to put the thing into text, and I'm going to try and keep the structure of that object in place so that when I send that object from the server to the client can just overlay the programming language structure on top of that blob and then get an object back. There's no parsing. And that's what a protobuf allows you to do. So you're basically, the notion here is this is derived from, so gRPC was derived from this protobuf, which was derived from this flat buffer. The idea here is what's known as zero copy deserialization. I have a structured object. I'm going to serialize it into a blob of bits. On the other end, I can deserialize that straight into my programming language object without copying it. It's sort of like a C structure. Like I save a C structure to disk, and when I bring it back, because the way C structures are done, it's just basically byte offsets that are assumed based on your structure definition. That's the idea here. But with this, you need this for every programming language, right? Like you need this, a version for Python, you need a version for Ruby, you need a version for all the different languages that you might do the exchange for. And that's what they have. So this protobuf, there's generators for C++, Java, C#, Python that will allow you to do this kind of transfer with zero copying natively. So that is where all of these, if you look throughout the Google infrastructure, Google will now give you an option. You can get the thing back in JSON, or if you want the thing to be fast and cheaper, then you would say, I want to access the gRPC version of that endpoint, and then you can save it that way. There's a URL here for when you would want to choose something like gRPC that you can read. One of the things that I'll note here is that for BigQuery, yeah, they make this mandatory, that you're using the gRPC version of their API. Okay, so the last part, and this is where your database labs are going to be, are SQL databases in the cloud. And we haven't really started the cloud stuff yet, but like the reason why I'm covering this kind of SQL database is because I don't consider this cloud. I consider this sort of legacy servers that Google is hosting for us. So Cloud SQL, AWS RDS, and Azure SQL databases, these are more for legacy databases that you just want to move over to the cloud. So the style of these databases are what's known as lift and shift. The idea is that, hey, I have a legacy application. All I want to do is take those machines and get them running on Google's data center. And so the easiest thing for me to do is to get my version of the database server, find the same version on Google Cloud or AWS RDS, and then just copy the table. And then I have a new IP address with the exact same data, and then it's just running on Google's backend. And this is happening everywhere. A lot of people are doing this operation, doing the lift and shift. So Google Cloud SQL is this drop-in replacement for MySQL, Postgres, and they also have Microsoft SQL. And so the idea is that you wouldn't have to purchase the hardware or install the software. You wouldn't have to reconfigure your code. You would just copy your data back into the server that you set up, and then be up and running on a compute engine instance. Is the idea. The equivalent is AWS's RDS, and so RDS supports way more databases, way more database backends. So again, you're specifying the database software you want to run, and then what it'll do is it'll launch an EC2 instance, install all that software on it, and then boom, you have an exact sort of replica of the machine that you are trying to remove out of your infrastructure, and then you have it running on RDS. Okay, so it's basically like you're just switching networks with the same old server stuff. So this is what I call this legacy cloud deployments, where you're not really taking full advantage of what the cloud can provide you. And so database labs number 1 through 3, the first lab is for you to get practice with SQL, with the insert intos and the select. The second lab is to deploy and interact with a Google Cloud SQL database backend. And then the third lab is to set up and interact with a AWS RDS backend. So those are your labs. And that is all I have for today. Are there questions? So finally, I give you some extra time at the end. So yeah, I'll be around to help you if you're running into problems with the labs for the rest of the time. But that'll be it for today.